Hello and welcome to the course Design Borefields with Confidence. This is the fourth chapter of the fifth part, and we will be combining the insights from the last three chapters, which was on the borehole resistance and the sensitivity related to that, as well as the sensitivities related to working with bore fields where the boreholes are defined with coordinates, so irregular borefield configurations. And we'll use those both insights to tackle one of the hardest and most common problems when designing geothermal bore fields, and that's the imbalance. Now, this imbalance, to recap, what is it? It's the yearly heating up or cooling down of the ground. And this is basically a consequence of your building load. If your building has way more heating and domestic hot water demand, chances are real that you are extracting more heat from the ground than you're injecting into it, meaning that you have a certain imbalance. If you extract heat from the ground more than you inject, the ground will cool down, cool down, cool down, and so forth. And we have two types of imbalances basically, and these are shown here. So on the one hand, you can have a ground heating up year after year. Think, for example, about warmer climates, where there is more cooling than heating demand. But in general, offices with data centers and so forth, they typically have quite a lot of cooling demand, so the ground heats up year after year. Now, in contrast, if you think about residential applications or colder countries, there the imbalance is typically going downwards, where the ground is cooled down year after year because, well, we extract more heat than we inject into it. And we do not want this imbalance because it drives up the investment cost. Because if your ground cools down or heats up year after year, well, we need to make sure that our bore field is sized in such a way that it can cope with it, that it will make sure that over the whole simulation period your temperature stays within certain limits. So it's better that we don't have this imbalance, but since it's a fact of life, it's a given for your building, we need to find ways on how to cope with it with design. And there are basically two ways to look at it. And we already said that borefield design, it has both long-term effects and short-term effects. And we talked about this extensively in part 2. And the thing is that for this question, although imbalance is something that we see after the couple of years, both the short and the long term are important here. Where the long term is indeed the downward going trend, as we discussed, and the short term is the difference between our fluid temperature during peak and our ground temperature. And both play a role. And we will discuss why now, starting with the long term and then the short term. Now, the long term, if you recall, it has all to do with G functions. And G functions, they determine how the boreholes interact with each other and in the end how your bore field behaves when a certain load is applied. And what is important is for these G functions that you want to place your bore fields as your boreholes as far away as possible, because the further they are away, the better they can exchange heat with the ground and the less impact you will have of your imbalance. Because if your ground can exchange heat better or interact with more ground because the boreholes are further apart, your imbalance, it will still be there, but it will be dissipated easier, let's say. So having a larger borehole to borehole spacing is important, but also having more open configurations. If you place your boreholes on a line, it's easier to exchange heat than if they are in a dense rectangle packed. And that's also basically what we saw in the last chapter when we were talking about the importance of working with the real coordinates of your boreholes and your bore field. Here we have these two different situations again. On top we had a rectangle, and although it's not very visible, you can see that this has an inner temperature contour in the middle of the borehole, which is the -6 degrees limit, whereas in the figure below there is no -6, there is only a -5 degree. So since the boreholes are placed further away from each other, or more scattered around, it's easier to cope with the imbalance than if they are all packed, because the cold gets trapped in the middle. Now, besides having to rearrange the boreholes and scatter them more around, Another thing you can do, and this has been done by the company Celsius Energy as well as Fraunhofer in respectively France and Germany, is to work with angled or tilted boreholes. Now, in the Scandinavian countries, this is already common, but in the mid of Europe, let's say that's not really the case. And it has a couple of advantages of working with tilted boreholes. Mainly in densely packed areas, you don't simply have the space to drill all these geothermal boreholes. And if you can start in one location and just drill around, like in a pyramid or in a star, let's say, well, then you save surface area. But also, since your boreholes are angled away, on average, they will also be further away, also lowering our G function in the end. And another positive aspect to this is typically you have a certain depth restriction in a country at 100 meters, for example, let's say. Now, if you drill vertical, yeah, well, at 100 meters borehole length, you will be there. However, if you drill under an angle, you can have more heat exchanger, a longer heat exchanger, for the same borehole depth, which is also good for, basically your short-term effects, because as we discussed in part 2, if we have more borehole meters, also the short-term effects will be smaller and your fluid temperature will be closer to your borehole wall temperature. So tilted boreholes is also a potential problem solver when it comes down to working with imbalance. Now, on the other hand, we have everything related to the short term. Now, the short term, as discussed already quite a lot of time, it has to do with the effective borehole thermal resistance, and this depends on single or W tube, as you now know everything about the grout, laminar and turbulent flow, and all these type of things. Now, the philosophy here is, why do we care about the short-term effects when we're talking about the imbalance, which is something on the long term? And the reason for that is that you can compensate or tolerate quite a lot of imbalance if you have a good borehole resistance. So this is an example of 5 boreholes with a borehole resistance that's not that great. It's 0.18 meter Kelvin per watt. And you can see after 25 years we reach our minimum limit. And in this case we have an imbalance of extraction dominated 15 megawatt hours per year. Now, if we keep the boreholes the same, the 5 boreholes in this case, but we make sure that the borehole resistance is better by increasing the flow rates, decreasing the viscosity, so changing the type of antifreeze, for example. We can also pump up the flow rate, increase the grout thermal conductivity, and so forth. And if we increase it or better it to 0.075 meter Kelvin per watt, well, our fluid temperatures are way closer to our borehole wall temperature. And these same boreholes can now cope with almost twice the imbalance, 32 megawatt hours per year of extraction domination, than the previous case. So, although the short-term effect has not an immediate effect on how the borefield reacts with imbalance, it can help us deal with it. Because if our heat exchange with the ground is better, the importance of the imbalance also a little bit goes away, or at least weakens. Now, another common practice solution is just say, okay, we have a certain imbalance, let's drill extra boreholes. Because the more boreholes we have, the more room we have to exchange heat with the ground, and again, this is better for the long-term effect. And in general, this is true. However, we need to account for a certain thing, and that's the borehole resistance. Because if we, for example, say we have 2 boreholes, let's say we drill a third one, well, the flow rate that was first going to only 2 boreholes now passes to 3 boreholes, meaning that chances are real that we were previously working in a turbulent flow rate, and now we're in a laminar flow rate. And if you recall what we said just a couple of minutes ago, is that if your borehole resistance becomes worse, it's also worse to deal with the imbalance. So yes, drilling extra boreholes is typically a good idea, but you need to make sure that your borehole resistance does not swing, does not increase too much, because then we we don't have a good heat transfer, and the imbalance becomes even worse. In fact, it's even possible, and perhaps it's a good exercise for you, to create this situation where you say, okay, let's add another borehole, and that due to this fact alone, that this extra borehole does not change the temperature in the end, because we just go from coping better with the imbalance from a long-term perspective to having a worse borehole resistance, compensating for that improvement. So this is something to really think about when you're just adding extra boreholes. And the other thing is drilling deeper. If you're extraction dominated, meaning that your ground cools down year after year, typically it's a good idea to drill your boreholes deeper. Because if you have deeper boreholes, your ground will become warmer. And if your ground is warmer, then all the lines will move upwards. So this means that you got a little bit more breathing room. Now, another advantage is if you drill deeper, perhaps you don't need as much boreholes, perhaps the same borehole length, total borehole length, but not the same number of boreholes, meaning that your flow rate per borehole will increase, which is also beneficial for the heat transfer and the borehole resistance, as we discussed already in the last slides. The thing is, drilling deeper is only a solution when we are working with extraction-dominated boreholes, because when you're injection-dominated and your ground heats up year after year, well, drilling deeper is not really a solution because your ground becomes warmer and it's even harder to get your heat into the ground. So this is only a solution when we're extraction dominated. And now to summarize this chapter and basically this whole part about the insights we can get when doing some sensitivity analysis and learn about how we can deal with certain problems, is that if you have a certain imbalance, what we know is always better is that we put the boreholes further away, and we can also tilt them to increase artificially, let's say, the surface area between the boreholes. We can put them in an open configuration, so not dense but more spread out in an L, a U, or a line. And also improving the effective borehole thermal resistance, like we discussed in the first chapter of this part, is always beneficial also when dealing with the long-term imbalance. On the other hand, we have things that are sometimes useful, namely to increase the number of boreholes, laminar turbulent is there very important. Keep that in mind, that you're not just adding boreholes and switching over to a laminar flow rate, because then chances are you're adding boreholes to just compensate for the worse effective borehole thermal resistance. And also drilling deeper is very efficient, but only when we're extraction dominated. So this was everything I wanted to say in this chapter. Please try to answer the questions of this part so you really understand what we're doing. And then in the next part, we will continue talking about some innovative probes designs, which will open up even more possibilities for your own projects. I'm looking forward to seeing you first in the answer video and then in the next part.